it is my honor to welcome our esteemed guest, Dr. Achintya Das, Senior Director and Head of Computational and Data Sciences and the Digital and AI Center of Excellence at Syngene International. We are truly grateful to have him with us today, and we deeply appreciate his time and presence. He will be speaking on the topic structure guided design of biologics using Molsoft tools. Dr. Achintya Das is a seasoned expert in AI and computational drug discovery, bringing over 25 years of experience in driving innovation across scientific and technological domains. As the Senior Director and Head of Computational and Data Sciences at Syngene International, he leads the development of advanced, cutting edge solutions that support modern research and industry needs. Let us welcome him with a warm round of applause.
I thought today I'll just give a high-level talk on what we do specifically on antibody design. I thought that's somewhere differentiated from how people typically have used ICM. And the reason behind our increase in interest in biologics is the fact that in industry there's a rising interest over the last decade or so on biologics. At Syngene itself, the number of biologics projects today exceed the number of small molecule projects. So hence, there is a push both internally as well as from clients for all the usual reasons. How do we shorten timelines for antibody discovery, enhance the quality and novelty of the designs, and improve success. If you look at the modeling domain, there is a challenge when you look at applications that are available for designing biologics. Small molecules have evolved over a couple of decades, but today, if you look around, there is just limited modeling software. Some of them are not very effective. There's not enough data, although the data is increasing in recent times. And the biggest challenge I have is lack of expertise. Most modelers are trained with small molecules, and you come with that small molecule mindset to attack biologics, doesn't usually work out. And if you look at why the landscape is such, small molecules are in a 200 to 5,000 Dalton range. Biologics are much larger. That increases the complexity, not just of the structure. The thermodynamics of biologics and their interactions are more complicated. You want to model them, you need a lot of computational power. Again, I come back to the training. Molecular modelers, every software or approach is trained by what I would call an atom-by-atom design in various ways. You can't think of biologics that way, so software also has to evolve. And if you look at data, if you look at protein structure prediction, for example, in the early 2000s, we were around halfway there, 50% or so. And today, you claim that you can build models which are more than 90% accurate. But if you see, the reason was the amount of data that was available for that. But you go to something like antibody humanization, data has been slow to grow, and look at the size of the data. We are just about to hit 95% or higher accuracies now because the data has grown. Whereas epitope prediction, which is key to do a structure-guided screen, for example, we are still around, let's say, around 70%, mainly because you just don't have enough data. Yeah. So even before you applied modeling, biologists have always used sequence-based method to design. It's always been there. Today, you'll be surprised of how many projects across the industry are done just by analyzing sequences. So there's a host of tools out there which work with comparing sequences, annotating them, extracting information from there. There are databases like ABCD, the IDB for immunogenicity, IMGT, host of tools online which basically are built upon rules that you extract from those. Then, of course, you have the molecular modeling tools. There's a host of suits out there, but very few actually address the antibody problem. And even within those, we've tried the few leading commercial software out there which claim antibody prediction, and over the years we've been burned badly. Let me say that. So I'll come to that in a moment. And then today everything is AI driven. People say I got AI driven antibody design. There was a company other day predicted 100% success in it. But it's still evolving. You can predict various properties, liabilities, but if you look at any successful or any effective AI design tool, they actually have a docking dependence. After the sequence is generated, they actually pass it through some sort of docking. So you actually need the complex of the antibody antigen structure for most of those what are called AI tools. So what does a typical workflow look like? You start by generating antibodies, hybridomas, NGS. From there, computationally, you'd like to look at to select what to take forward. You look at diversity. Sometimes, or actually quite often, people look at patents, look at antibody and say, what can I do around it? So you redesign the CDRs. De novo antibody design is still not there, but people do try it nowadays. But that's not the main way that people do screening right today. Now, once you have that, you then start looking at what is the lead and that you take forward to develop further. Mostly, you develop those antibodies in some non-human species, either rabbits, murine. Nowadays, you have llamas and all for it. So those need to be humanized, or if you're starting with a human a redesigned CDR around human antibody, then you do some in silico mutagenesis, make some changes on various residues to say, okay, this is going to be my lead, and those are typically driven by some affinity estimations, and then looking at whether it's amenable for human for human use by looking at immunogenicity. Once you establish a lead, then you start looking at how do I make that a candidate. In the lab, it's called affinity maturation. You can do that in silico by generating doing a lot of mutations simultaneously, looking at which are the highest affinity ones, and then taking that further. There are a lot of formats now. Antibodies are done in various formats. You can do SCFVs, there are BITE and other formats. So if you have a preferred format for the modality and the therapeutic area that you're looking at, there's a lot. This is a time when you also reformat it into the way that you'd like to have the antibody. And then to develop that further, the antibodies might aggregate like any other like peptides, or you don't want that. There might be PTMs or chemical liabilities, amidation, oxidation, glycosylation sites, etc., or stability, both colloidal stability, physical stability. That might when you develop that further and start scaling that, taking into development, you'll have issues. So you want to get rid of that early. So putting all that together enables you to go to a lead candidate. Sorry, yeah. So what we used to do earlier over the years is basically use a diffusion model that's from Rosetta, basically Rosetta fold diffusion model that rapidly generates structure. But docking and scoring, antibody antigens is quite complicated, hard to get, reliable models and scores. So we used to, the only thing that we've tried, as I said, various softwares, and the only thing that worked over the years has been Rosetta. The problem with that was its intensive computation takes a long time to get decent results that you then carry forward in lab. So the problem that we faced was nothing wrong with that. Compute intensive, so we're doing multiple projects, it was just difficult to scale. And the biggest problem, Rosetta is not easy to use. And with all respect to current generation modelers, once this concept of, clicking buttons to do modeling came up, people just forgot to use traditional software, and I have a huge challenge on getting people to adopt and get trained on Rosetta. So when we had ICM, so I said either something that we can do to use what you have in the protein docking in ICM and build a workflow that can alleviate that. So what we did was, we still do structure generation using RF diffusion. That's pretty fast. Instead of docking and scoring in Rosetta, we basically, from the diffusion model, collect a host of diverse structures. We do not pick any one, but pick a set of generated structures from there. Use that for protein docking in ICM. Mind you, that's basically the difference is that if the FFT there is basically rigid body docking, which is why we take a number of poses rather than taking one. And then from that, select diverse poses. We rescore that with a MMGBSA based approach. It's a trained, it's a variation of MMGBSA, because what we found was the scoring from there wasn't perfect. It's not trained for antibodies basically. So after doing that, we sort of looked at 10 older projects and said, how does this perform? We found that the correlation between what used to do earlier and with ICM is more than close to 95%, but at half the time. So that was a huge advantage for us, and now we do most of our work in antibodies this way. The second problem that you have is immunogenicity. Many projects start with humanizing, even though you have transgenic mice nowadays. Still, a lot of companies still prefer to go the traditional route of humanizing. So, what do you mean by what do you do during immunogenicity or humanization? So, if you are developing the antibodies in something that is non-human, if you administer it to a human, you will get immune response, because that's something that your immune response will respond to. So the idea is to remove all those epitopes that can basically cause responses, immune responses, so that you'll have a safe antibody. Typically, if you look at what people do, you start comparing with known immunogens or MSC binders. There's a database called IEDB, immune epitope database. A lot of people do comparison there, and there are some models there that predict MSC binding. You predict MSC binding by using machine learning models or matrices derived from conservation as well as from binding. And then you end up actually getting a lot of false positives. Although it may be immune, your body might have seen that earlier. So you do a cross-conservation analysis by looking at TCS and the human proteome, and then rule out those false positives. That's the typical workflow that people follow. The problem we had on our projects is, in 90% of the cases, we had unnatural amino acids. because of various modifications. The other problem we had is after the post discovery, when those are being developed, manufactured, you always have impurities which have unnatural amino acids. And then for regulatory filings, people came to me and asked, can you predict immunogenicity? None of these methods actually work. So, and the traditional way people have been doing is you replace that by the closest natural amino acids. Some companies went forward, and FDA had a problem with that. Then companies like Epivax and all said, oh, why do it by only the closest? Do it with all 20 amino acids. So you say, okay, does it matter which amino acid it is, still going to be safe or not? It's a very questionable way to do it, and people have shown that by that method you did miss certain sequences that had unnatural amino acids. They elicited ADS, but you missed that by doing this. So again, we thinking like a molecular modeler said, oh, you're predicting binding, so why not look at it from a docking point of view? So what you did was pulled out around 13 common MSC alleles that are typically used for predicting or looking at MSC binding. Extracted some of those structures from the PDB. For a few of them, we had to model the structures. So we created this, models of those 13 alleles, and all test peptides that you extract from those sequences, we dock those to those alleles, and then the pose. So the way that immunogenicity elicited is that you first bind to MSC, and then you have to have a surface where the TCR has to come and bind. If that's not there, we will not elicit immunogenicity. So the poses are selected. We have a rule-based method which looks at how well you bound to the allele, and do you have the surface for TCR binding. So using that, we pick up the poses and take their scores. And if you see on the graph there, the bottom two are Padre and SARS-CoV-2 highly immunogenic sequences. The green one is lanreotide. It's a safe therapeutic in the market. So what we found was that if we took highly immunogenic sequences and clinically approved peptides, we actually saw there was a marked separation between them. So now what we do is you basically look at the docking profile of any test compound, see where it lies on that scale, and then combining that with the cross conservation with the human proteome, we are able to score those. So it's a docking approach that replaces the traditional sequence-based MSC allele binding, and this does not have any dependence on the type of molecule, even whether it's natural or synthetic. And over the last 3 years, we've done a host of regulatory filings, not just for us, but when I say us, our sister companies, and also for our clients. And it's been approved by both US and European regulators. So that fast scoring for docking and selecting the hypothesis that you want to take into testing, combined with the machine learning models that we have for all the other liabilities, that now enables us to support the design, make, test, analyze cycle for all our antibody projects, where they are for antibodies of various kinds, whether ADCs. So any modality now, we are able to support that because we are able to screen a large number of constructs and then push that through the cycle to and then do a multi-parameter scoring to send them for expression and testing. So I will end by a case study just to show how that works. this is a project we did for a large pharma company. So they had this mouse antibody, which had nanomolar affinity for 5 chemokines in mice. So the challenge that we given was humanize that and give us high affinity for all those 5 chemokines in human. So typically when you get such a project, the humanization goes by, you first graft that into human. So you take the CDRs, you you find the closest human framework, and then you graft that on that. Now once you get that, the CDR itself might have immunogenic issues. So you start to germline that. What's the minimum changes that I'll make so that it will be less immunogenic in humans? And then you need to look at whether the orientation of the CDR is right on the framework, or probably you have to do some back mutation so that is required. Otherwise, you will not get binding. So once you do that, now you have a humanized version of that antibody. Then you start looking at how do I still improve the affinity, the post-translation modifications, all the chemical liabilities, because you don't want it to cleave, we don't want oxidation, imidation, etc. Developability in terms of aggregation, electrostatic parameters. The PI is very very important when you look at scaling up. And then you arrive at a candidate that you'll take forward. So it's just a reiteration of that cycle that I talked about. You start by generating structures, then those are pushed into the ICM FFT docking, score it with a scoring function, look at the developability liabilities. There should have been arrow to assess the designs. Then it goes into a multi-parameter score, which scores that along against all these parameters. You carry out mutations on that, and you run the cycle, take the top designs. So doing that, when we humanize the antibody, that first, these are the experimental binding values. So if you see the first row, when you humanize that, well, we removed immunogenicity, but it wasn't ideal, ideal in terms of affinity. Then we, the next round, we prioritized 10 constructs for testing. Out of those 10, 2 met the project criteria. So that this was like the whole project was completed in 2 cycles. We achieved it. So the point I can to be made is that you can't identify this is the one that you take. In this case, out of the top, prioritize the 1 to 10, 2 and 6 were better than 1, 2, and 1, 3, and 4. So what you have seen is on this, if I can bring the whole project down to around 10 to 15 constructs that we give in every cycle, and we generally hit the product profile. So we have applied this for designing antibodies, reformatting antibodies from one format to the other, improving properties of antibody. Recently, we finished a project where we made the SCFV BBB penetrable. What you do with ICM, it's not that you can't do it. I mean, you can always identify a rigid body docking, protein docking somewhere, and there are lots available on the internet and all, but that enabled us to do this more rapidly. May not be perfect, but it just works. If I had more computation, maybe later we do a more evolved version of this. But we continue working on improving our workflows in biologics. But yeah, this is where we are. Thank you.
A heartfelt thank you to Dr. Achintya for his remarkable talk. Thank you, Dr. Das, once again for your time and esteemed presence. It was a privilege to host you. I would now like to invite Mr. Surajit Sadhu to present a token of appreciation for our guest,